Greetings. This is Chapter 14, Part 1 lecture. And what I want to talk about is buffers. Buffers are the topic of Chapter 14. Now, what we want to remember is that acids are abbreviated by this kind of generalized formula, HA. Okay? And this guy here is usually aqueous, like acetic acid or nitrous acid or lactic acid, and they have different formulas. And this is in equilibrium with protons, or the hydrogen ion. And that's, of course, the business end of an acid, and the conjugate base. Okay, so we call HA the acid, and we call A minus the conjugate base. All right, and this is the generalized equilibrium. Now, the equilibrium constant for this is called Ka, as you remember, and A is for the acid. And that's going to be equal to products over reactants. All of these substances are aqueous, so they enter into the equilibrium expression. They all have coefficients of 1, so they're all to the first power, which we, of course, don't write, just to simplify the expression. So it's always products over reactants, and this equilibrium value is quite small. So one of the things you can do is look at Appendix 3, which lists out the Ka values for your different acids. So the Ka value for lactic acid, for example, is 1.4 times 10 to the minus 4. You can find this on your lecture guide on page 58. Page 58. Okay. And I want to work with lactic acid here just to show you how to use it. So if you were asked to describe the equilibrium for lactic acid, you would go like this: HC3H5O3, okay? And we've discussed why there's hydrogen in different locations. There's hydrogen here, which means it's monoprotic because there's just one of those, and the rest of all these carbons, hydrogens, and oxygens are all bound up together in a covalent large molecule. And this guy here can be in equilibrium with H+, and we can remove the conjugate base off of that, and we get this, okay? And what we can do now is write the equilibrium value for this. Ka is going to be equal to products over reactants. So it's going to be H+ times C3H5O3 minus over HC3H5O3. Okay, so that's the two products are up on top, and the reactant is down below on the bottom, and they're all aqueous, and they all have coefficients of 1. And this value, according to the table, is 1.4 times 10 to the minus 4. Okay, it's quite small, which means that reactants are highly favored. Products are disfavored. And in a solution of lactic acid, whether it's 1 molar or 0.1 molar, you're going to have mostly associated molecules. Okay? And very few ionized molecules. They're called ionized because they're ions. And the percent ionization might be, 5, 6, 10% or something. Now remember how we talked about doing this in the previous chapter. We've talked about ice tables. So if we have our lactic acid here, and it can dissociate ever so slightly to give H plus and the conjugate base, which is lactate. Okay, and we want to know, what is the percent ionization. We can do this by setting up an ice table, okay? And you can plug in whatever value you want here. I'll plug in 0.1 molar, okay? And we assume that very small amounts of it ionize to produce very small amounts of these ions, okay? And what we can do is take these equilibrium values from our ice table and plug it into that equilibrium expression up above. And so that's going to be x times x over 0.1 minus x. And remember the assumption, we assume that x is small. So we assume that 0.1 minus x is about equal to 0.1. And so what we get from this is 1.4, 10 to the minus 4, equals x squared over 0.1. And on our calculators, if you punch that in, you get 1.4 times 10 to the minus 5 is equal to x squared. You take a square root of that, x is equal to 3.74 times 10 to the minus 3, okay? The percent ionization is the amount of A minus over HA, right? The amount of ions per unionized associated acid. So that's going to be equal to this ratio, 3.74 times 10 to the minus 3 over 0.1, right? We multiply by 100 in our calculator to convert that to a percent, and what I get is 3.74%. Since this acid is very little ionized, we say it's a weak acid. Since there are very few ions in solution, we say that it's a weak electrolyte. Okay, let's do another practice problem. Write the equilibrium for Ka of hydrocyanic acid. Here's HCN aqueous. And see if you can write the Ka for this, okay? So write the chemical equation and then write out what the Ka expression is equal to, okay? The third thing is to calculate a percent ionization. And the fourth thing is to compare that with lactic acid. Is HCN a stronger or weaker acid compared to lactic acid. Okay, and you'll enter these into your worksheet.